Good day, dear colleagues. And thank you very much to organizers and Volodya for inviting me to this conference to memory Professor Baxter. My talk is, the subject of my talk is construction of heterotic string. Heterotic string theory compactified on Calabi-Yau manifolds of Berglund-Hubsch type in the Batyrev-Borisov combinatorial approach. First of all, I would like to tell a few words about why we need to heterotic string theory. Four-dimensional heterotic field theory compactified on Calabi-Yau manifolds. The reason is that the string theory is the only possibility to get quantum gravity, quantization of gravity known until now is namely string theory. And also we need namely heterotic string theory to get it's you see is a few lines why we need what we would like to know how to construct quantum gravity, how to unit three interactions of elementary particles, how to unify them with gravity invitation. And the heterotic string theory in 4 dimensions consists of two conformal field theory. In left moving part, we have one fermionic string theory with central charge 15, and it is product this galomorphic conformal field theory. Left moving string theory is a product of two conformal N1 conformal field theory, which consists of 4-dimensional N1 string theory and the other part is N equal to superconformal field theory, which correspond to compactification on Calabi-Yau manifolds. What about antigalomorphic right-moving part is of this hybrid is a right-moving bosonic string theory with central charge 26, and it consists of is a product of a few conformal field theory, 4-dimensional bosonic string bosonic string, and other 22 dimensions correspond to compactification on again on Calabi-Yau manifolds, also on the product of torus E8 Lie algebra and SO10 Lie algebra. The important class of exactly solvable heterotic string models was constructed by Kepler many years ago. As it corresponds the product of n equal to minimal models with total central charge 9, and it is equivalent to compactification to Calabi-Yau manifolds, which belong to some special class of Calabi-Yau of Berglund-Hubsch type. In this talk, I am talking about generalization of this construction to all cases of compactification Calabi-Yau manifolds. Calabi-Yau manifolds on general Berglund-Hubsch of general Berglund-Hubsch type. For this purpose, I use the Batyrev-Borisov combinatorial approach to construction Calabi-Yau manifolds of Berglund-Hubsch type. And also to get the result, we need to do a few additional, a few reduction. One of them is usual PRST reduction in left and right sector, and also a reduction which correspond to which needed reduction in left sector, which is needed to get n equal 1 space-time supersymmetry. We need, namely, smallest we need to get smallest supersymmetry, and we get it in left sector. And we need also, we want to get also the extending of standard model to grant unification, and we get gauge symmetry E8 multiplied by E6 algebra after some similar reduction in the right sector, anti-anglomorphic sector. And the result, we get super multiplet of gravity, a super multiplet of vector fields, gluons, and other. And we get also material sector 27 and 27 bar representation of E6, which includes quarks. Quarks and leptons, not gluons. It's a mistake. And we have also a singlet. We get also singlets of E8 and E6, which the number of types of this singlets is defined also by the property of Calabi-Yau, namely, it depends. It is determined by the data of mirror reflexive Batyrev polyhedrons, which correspond to given Calabi-Yau. Okay, this method to use Borisov-Batyrev combinatorial approach is realized by free bosonic and fermionic fields. And the construction uses requirement mutual locality left moving vertices of n equal 1 supersymmetric generators, and in right moving part mutual locality with generators E8 and E6 gauge symmetry appears in the right sector. And after this, we require the mutual locality of products of left and right vertices of which correspond to physical states when each of other together and other requirements of conformal bootstrap, and it leads us to self-consistent result for namely for the case when we do part of compactification on product torus of E8 and SO10. It is the only possibility, and we get in result then extending of S10 to E6, and it is the gauge group which is needed for our goals. The construction starts from a product of two conformal field theory. In left alomorphic side, we have n equal 1 superconformal field theory. In right antigalomorphic side, n equal 0 conformal field theory. In left sector, we have we have the product of two conformal field theory, four-dimensional conformal N1 conformal field theory for subsector of space-time with central charge 6, and n equal 1 conformal field theory for compact Calabi-Yau subsector with central charge 9. So the total charge, central charge is critical. It is equal 15. N equal 1 conformal field theory in left subsector is a theory of which is construction is used for bosonic fields X mu and for fermion fields Majorana fermions psi, like usually, but the number is 4 and 4. In Calabi-Yau subsector in left part, and also the same in right part, we have a subsector with central charge 9 and some 6 here. Central charge 9 is 15. Critical central charge is the theory of free bosons X plus minus and Majorana fermions psi plus minus is the number is 5. The algebra of vertex operator in this subsector is defined by data of Calabi-Yau manifolds of Berglund-Hubsch type. I will explain later this. In left moving energy momentum tensor is this sum of from space-time sector and tensor energy momentum tensor of Calabi-Yau path. In right sector, we have the product of 4 n equal 1 conformal field theory. It is a conformal field theory sector with central charge 4 realized by 4 bosonic fields X mu of Z bar. And also we have E8 subsector with central charge 8 realized by 8 free bosonic fields Y E. I is equal 1, that's 8, compactified on torus of E8 algebra. Next sector corresponds to conformal field theory where the fields we have 5 bosonic fields phi alpha, and bosonization they leave these fields, they live on torus of SO10 algebra. And at last, the fourth sector is Calabi-Yau subsector with central charge 9, and it looks the fields like in left sector. The total the total central charge is 4 plus 8 plus 5 plus 9 is equal critical number 26. Conformal field theory in Calabi-Yau sector with central charge 9 is realized like in left sector. Okay, now I tell about Borisov approach to construct n equal 2 superconformal field models by free fields, free bosonic and fermionic fields, which it gives us for construction of these models with central charge 9 n equal 2 superconformal field theory model with central charge 9, we will use the data of some Calabi-Yau manifolds of Berglund-Hubsch type. But first, how it's written how we define the the generators of n equal 2 for this case. We have 5 fields, C plus and C minus I, bosonic fields, Marian fermions fields, which has this operator product expansion, and also we will use bosonization of bosonic fields like it's written here. The currents of for the currents for looks like it's written here, and if we see that there is the coefficients a plus minus I here, if they have is equal equal 0, we get usual realization for n1 super algebra with central charge 15. But following Natsenko-Fateev, we add these terms, this, and this in all 4 currents, and we get the central charge 9 in the result. Namely, we do it as the following. We choose vectors A plus and N minus, which defined by a chosen Calabi-Yau manifold. I will explain below how we define these vectors. And then the scalar product of these 5-dimensional vectors is equal 1. Therefore, the central charge, which is defined of this formula, is equal 9, like we need. Now, how to what is the connection between Calabi-Yau with central charge 9, which correspond to n equal 2 superconformal field theory with central charge 9. This Calabi-Yau is defined like surface in weighted projective space. With the weights is written here, and by this equation, W is polynomial, not degenerative polynomial, which looks like this, and the integer matrix of exponent is defined. The requirements that it should be Calabi-Yau manifolds and has one of 16 types of Berglund-Hubsch type. It is satisfied to this 5 equation, this exponents, and polynomial is invariant in respect to some under substitution, and this we will consider simplest case when symmetry group is minimal, admissible simple group. Generator of this group is looks like it's written here, and okay, the mirror manifold is defined by mirror polynomial W T, which is a transport matrix of AT. in GT in mirror projective space. Okay, now from this data, Berglund-Hubsch data, we and in Winslow group, we obtain Batyrev-Borisov combinatorial data in the following way. We define first two lattices, 5-dimensional lattices, M0 and N0, with basis 5 vectors Ui and 5 vectors Uj, whose pairing it looks like this. The solution of this pairing is written here. And then we define vectors A plus, which I used before, A plus and A minus, which is looks like it's written here. And then we can show that their pairing is really equal 1. The next step is to extend lattices M0 and N0 to pair of dual Batyrev lattices M and N. For the case when group G for polynomial is minimal. I consider now this case. First, we extend the lattice N0 like it's written here, such that it includes vector A minus. Then next step we find bases, 5 vectors in this lattice. Then we define the basis of dual lattice M from this equation. And after we get these two dual Batyrev mirror lattices M and N, we define the Batyrev polyeders, delta plus and delta minus. Delta plus is a polyeder which lives in lattice M, and delta minus N. And these polynomials, by definition, is defined as the finite number vectors M and vectors N satisfied to the equation which I can see, but maybe you can see it. Can you see this equation? It's my question. Леш, видно?
Yes, we can see it.
Потому что у меня it's
no, it's totally fine.
Stop it. Okay. Okay, now then. Okay, I understand. Now we can define using the elements of these lattices, this polyeder, Batyrev polyeder M and N. We can use it to define the set of differential dm and dn. It's written here. They satisfy to this equation. And we will impose the following condition on the vertices, on the states of. First of all, of course, because it's string theory, we have to the physical vertices, physical states should be BRST invariant in respect to BRST operator in left and right hand side. But also we require that they should be a cohomology of all this differential. It is. I think that it should remind when we construction of minimal representation representation in minimal model says this requirement. So we have vertex algebra in our construction, and this algebra, the Virasoro in left and right side acts on this algebra, and we impose up to now we impose to restriction of this space of states, BRST and this generators. Okay, then in result we get some restriction for this vertex operator, which looks like some polynomials of derivatives of our fields, which this field is written only the fields which correspond to vertex part of vertex algebra in Calabi-Yau sector. It is X plus and X minus fields, and H is bosonic fields which correspond to Majorana fermions, and it is a dimension of these vertices. And there is some restriction, but I will skip it for this, for NS sector and for Ramon sector in left part, which is written here. Okay, and so we call this subset of states which belong to intersection of BRST cohomology set and Borisov cohomology. I will name them the space of quasi-physical states, not physical yet, but quasi-physical states. But below we will perform two more additional reduction of the sets. In left part, in galomorphic part, we find the vertices which can be used for which belong to Majorana representation of Poincaré, and which can be used to extend Poincaré algebra, which we have in left sector up to N1 super Poincaré, adding some integrals of some vertices which belong to this representation, and so we have generators in left sector. We have generators for n equal 1 super Poincaré algebra, and we demand. We require that the left part of vertex operator should be invariant, mutually local with these generators, and there's some restriction of this. And the same we do in the left-hand side. In left-hand side, in the result we get from E8 and SO10. Generators which appears in right-hand side because compactification to torus of E8 and torus SO10, adding some spinor representation, we can get generators of E8, E6, and then impose again restriction on the right side vertices to be locally, mutually local with respect to the generators. It is the next steps. Okay, now what I return to left sector. Left sector consists of the product to N1 super algebra, and one correspond to space-time sector, and it is realized by four bosonic fields X mu, and four bosonic fermionic fields C mu. And also we have Calabi-Yau subsector, and with this, which is realized by these fields. We choose diagonal subalgebra, and one subalgebra its currents is defined here. It is sum of currents in space-time and Calabi-Yau part, and n equivalent Virasor algebra is correctly defined on the product only an S representation and product of only in one subsector and other subsector Ramon representation. I skipped it. It's about definition of ghost. In the result, we have Berester operator in left hand side. It consists of currents of matter and ghost, like usual. And in left-hand sector, we have vertices, which looks like it's written here. We have this term for in vertices, which consist of depend on the derivative of the fields defined above, and this exponent, which is written explicitly here. It is written the expression for dimension in the excerptor. It is phase when we, which is expression which is needed to understand to get mutual locality of two fields, and okay. I have to. I think that I have to finish already. Volodya.
Seems like
how much I have.
You already spent 5 more minutes, I guess, something like that. So
Okay. So I think I have to stop. I have to show the result. To tell what is the result of this construction. It is written the field, the supercharge which extend Poincare to super Poincare. It is some restriction for vertices. It is tensor, the fields, energy momentum tensor in the right hand side, and again here we get first we get generators for E8 and SO10. Then we do using spinor representation and of SO10 and one-dimensional one representation in sector Calabi-Yau sector. We extend SO10 to E6 algebra, such that in result we get a product of E8 and E6 algebra, and then we restrict the space of quasi physical states, quasi-physical vertices and leave only those which mutually local to this symmetry in left and right hand sector, and in result we have then we construct product of this left and right, and again impose a requirement to be mutually local between themselves. It is possible, and it gives us the set of physical fields already, and and in result, we get four in this set of physical fields. The most important for physical application, most important are massless fields. Massless fields, which correspond to particles like quarks, gluons, and so on. Some of them massless get mass, not which is not zero. Some of them is, but they are the most important, and we get four multiplet: gravitational multiplet, gauge multiplet of E8 and E6 algebra, and supermultiplet gauge. It's the second. Third is material supermultiplets, which is a number of 27, representation of E6, and a number of 27 bar supermultiplets, and the number of these multiplets is defined by is equal the number of points in Batyrev polyhedra, 27 1 and 27 bar, the number of mirror. And at last we get singlets, which correspond, like we can expect, dark matter. The number of these singlets, which are neutral in respect to E8 and E6, interaction. The number is the number of pairs of mirror pairs for given Calabi-Yau manifolds, such that the product of vectors and in vectors belonging to one Calabi-Yau and polyhedra initial Calabi-Yau and mirror Calabi-Yau has product scalar product 0, and okay, so yes, and this result was compared with the result of Gepner, who did the construction of Heterotic field on minimal models, and the results coincide. Okay, thank you very much.
Thank you very much.